So we would like to discuss the notion of connectedness for subsets of C, in particular for open subsets of C. We recall that a set D of a subset D of C is called open if for every A in D, again, this means belonging to, there exists a delta greater than 0, so that the open disk centered at A with radius delta, so that's all the complex numbers that whose distance from A is less than delta, is a subset of D. Okay, of course, this delta depends on A, and the closer A is to the boundary, the smaller you have to take this delta. I mean, if you are in the interior, or at least if we have a picture similar to the one I drew, then you can see that there are points for which this delta can be chosen to be larger. And complements of open sets are called closed. So K subset of C is closed if C minus K, which is pretty much all the points that don't belong to K. So these are all the Z in C such that Z does not belong to K, is an open set. Closed sets, here we shouldn't get tripped into believing that a set is either open or closed. Most sets are neither open nor closed, but closed sets can be also defined in a way that has nothing to do with them being complements of open sets. We can just say that it is true, so fact K is closed if and only if whenever Zn is a sequence of elements of K with Zn tending to Z, then Z belongs to K. So in other words, K does not let its sequences converge outside of it. Such a set is closed, and it's the complement of an open set. Now, we would like to talk about connectedness, and in particular about connectedness of open sets. So an open set D, subset of C, is called open. I'm sorry, it's called connected if it cannot be represented as the union of two open, non-empty disjoint sets. Disjoint means that they have no elements in common. I.e., one cannot find U, V open with oops, sorry, my pen is acting up a little. So with U different from the empty set, V different from the empty set, U intersection V empty, and D being equal to U union with V. So in other words, a connected set cannot consist of two or more disjoint pieces. So a set is not connected if an open set is not connected if you can find two open sets or two or more that are disjoint and their union is U. I'm sorry, is our set. So for our purposes, there is a very interesting characterization of such sets. So a set, an open set D is connected if and only if for any 2 points Z and W in D, there exists a polygonal line that is fully contained in D and starts at Z and ends at W. Okay, so what does this mean? You have an open set. It's connected if for any 2 points in that set, you can find a polygonal line. So a polygonal line is a line that consists of line segments that starts at the one point and ends at the other point. Here we should add that polygonal lines consist of line segments, and a line segment in C is the image of a map, meaning of a function, R of t equal to 1 minus t times z plus tw for t between 0 and 1. Let's see what this means. This means that, let's say here's z, here's w. If you want to ask what are these points, these are exactly the points of the line segment that connects z with w. In particular, if t is 0, we get z. Indeed, plug in 0. You will get z plus 1 times z plus 0w, so this will be z. And r times 1, I'm sorry, r of 1 is w. Okay, so if we can put such segments one after the other so as to go from any point of an open set to another point of the same set, then we have a connected open set. Okay, so that's all.